So we can now start, and it's my pleasure to introduce Rita Fioresi from the University of Bologna. And Rita will talk about quantum principal bundles over quantum projective varieties. Rita, up to you.
Okay, so Stefan, thank you, and thank you also to Ivan for this invitation. It is very nice to be able to share some quantum mathematics with all of you. Now, let me... Okay, now it's not working anymore. Ah, no, okay, right. Okay, so as Stefan noticed, there are three logos because I am the PI of 3 European projects. But 1 minute to advertise one of these projects. It's called Callista, and you're very welcome to join it. There is a non-commutative geometry and quantum homogeneous spaces working group. And what happens if you join? We give you money. What happens? I mean, what are your duties? None. In the sense that you don't have to pay to join. It's all free, and you can apply for grants and get some Callista money, and we'll be very happy to share it with you. So please apply, please join, please write grants so that we can fund you. And this is especially for young participants. I mean, of course, we fund everybody, but we give precedence to postdoc, graduate students, people that don't have a permanent position. Okay, great. Write me about it when this talk is over, if you want more news. Okay, so let us start the talk. I'm talking about quantum principal bundles over quantum projective varieties. So let me try to first establish what I consider what type of varieties I am considering. Not just any projective variety. I'm looking at quotients of complex algebraic groups, which are semi-simple. So we take G, a complex semi-simple algebraic group, and these are well known. For example, SLN is an example of such group. Then we take a closed algebraic subgroup, and we assume it to be parabolic. What is parabolic? For example, if you take SLN, you take the upper triangular matrices. That's an example of a parabolic subgroup. It's actually more than that. It's Borel is an example of parabolic. Parabolic a little more general, but we will see examples later on. And then we fix a character of P. We take... I am so sorry, my phone will not... Oh, somebody's saying is having trouble to connect, whatever. Sadly. Let's take a line bundle on the quotient of G mod P. There is a construction allowing me to build a line bundle once I'm given a character of the subgroup P. We're going to quickly review it. I call the global sections of this line bundle with this strange notation, OG mod P1. I will explain why it is called like that. I look at all functions from G to C, so these are the polynomial functions over the group, which transform according to the character chi. So in the community, looking at Hopf Galois extensions and so on, we're looking at invariant functions over quotients. Here we are looking at semi-invariant functions. So they're not really invariant per se, but they transform according to the character. So you multiply by a constant, okay? This, not a constant, by this chi minus 1h. And if you have such a line bundle with a condition of being ample, I will not dwell into this, we obtain a projective embedding of this variety, G mod P, which is a projective variety. And actually, one way of characterizing parabolic subgroup is exactly this, to say that G mod P has a projective embedding. And we can build the coordinate graded algebra associated with this projective variety. So this algebra is obtained by summing all the, is a direct sum of all the homogeneous components, and this will transform according not just the character chi minus 1, but chi minus n. There is a plus and a minus, depends on the convention. I will not enter into it. Some people put just the plus. It is not important. So this slide is to tell you what is the commutative setup we're after. Let us look at the very instructive example, because this example is the projective space. So the projective space is obtained as a quotient of the special linear group with n equal to, and the Borel subgroup, that here is played by the role of P. The upper triangle is the parabolic. Now, we define the following character. So we take any triangular matrix, we associate a to the minus 1, and then we build the line bundle. I'm not writing the explicit, it's not difficult, but I didn't want to spend time on this. It's just, well, if you know this construction, it's just all the pairs of, G and a complex number modulo a suitable relation. Now, if you look at all the functions that transform according to the character, you'll find out that these are exactly the function A and C. I put an hat because I just wanted to distinguish between a function and an entry of a matrix. But to be honest, people just write A instead of a hat, whatever. And in fact, you can check, is a very fast calculation, that if you consider the function associating to the matrix product of ABCD by A prime, B prime, 0, and D prime, you obtain A prime, the product of the first entries. And if you play this game, put in the character, you get the same result. This is a trivial calculation, but it is very instructive, because actually this is the key of all the construction. You are building the ring of the projective embedding, starting from the semi-invariant functions, in this case A and C, and you are building all the semi-invariant functions starting from a very special one. I'm going to comment on this. So this example shows to you a method, but suggests more suggests more ideas. Let me go to the example of the Grassmannian. So the Grassmannian is the quotient of two spaces in a 4-dimensional vector space. Is the quotient of SL4C modulo this parabolic that looks very similar to the Borel we saw a moment ago. But here ABCD, R and 0, are 2 by 2 matrices. So this is the expression of a block matrix. We define the following character. Is exactly the same construction that we did before. We take in the matrix AB 0D, we take the determinant of A to the minus 1. Again, the sign is appearing because depends if you're looking right or left action. It's not crucial. And then we look at the semi-invariant functions, what I denote here with OG241, okay? And what you can show is that these semi-invariant are all the determinants obtained of the minors, obtained by looking at the first two columns of SL4 and any two rows. So are special minors. If you look in books, people may take the rows instead of the columns. That's, again, a choice depending on left or right action. Now, this you probably have already recognized that this is giving you the Plucker embedding of the Grassmannian into the P5, okay, through the determinants. And what you can do, you can translate the conditions that we have given of semi-invariance in terms of algebraic terms. So we wanted a certain product f of g times h equal to chi minus 1 h f of g. You recognize that dually you take the co-multiplication of the element and you tensor by, and you wanted the, so invariant would be f times 1. Semi-invariant is f times chi minus 1. So far, so good. Are there questions? I guess we are happy. Stefan, you can hear me all right? You can see my slides?
No problem, Rita.
Okay, great. Okay, so suppose we have a G mod H, very general. Actually, I should say G mod P. I use the parabolic. Then there exists an element T which projects to the ring of H with the following property. And this T determines uniquely the line bundle, and so the projective embedding. So essentially what I'm trying to say is that this very simple property over here will fully determine the line bundle and the projective embedding of the variety G mod H or mod P. I'm sorry, this is a typo. This fact is a classical statement, possibly known to the algebraic group people, but we could not find it in any way. But for us that are doing non-commutative geometry, is a very precious statement because it allows me, just by knowing one element of CG, to define the quantum ring, the quantum graded ring of a projective quantum variety. So let me give you an example of what I mean before I give you the definitions. So assume that you are looking at G24, the Grassmannian, and we look at the Plucker embedding. So this element, this magic element T, is the determinant of the principal minor of the matrix of SL4C. And indeed, if you construct the ring, it will be the ring generated by all the minors inside the ring of the group G, in this case SL4. Now, how can you derive all the minors from this T? I will explain this in a moment. Probably you can guess it, but let's not go ahead of ourselves. Now we are going to quantize this object, this element T, and we will show that we will hand out immediately quantum homogeneous projective spaces or projective varieties. Not only this, but it will be instrumental to produce a quantum principal bundle over such varieties. Okay, so we go for the quantization of this object. First of all, what is my setup? I look at CQ, which is the ring, the field C to which I add the indeterminate Q and Q minus 1, its inverse. One may also consider Q as an element of the field. There is no difference in the treatment, but okay. For me, a quantum group is just an Hopf algebra over this ring, which is torsion-free as CQ module. And I want to give the definition of a quantization of an algebra. It's a very loose definition. I take again a torsion-free with the condition that whenever I quotient by Q minus 1, I reobtain the algebra I started with. Now, the problem with projective varieties is that, as we well know, there is no algebra strictly commutative, strictly associated with it. What do I mean? We know that for an affine variety, for example, if I take an affine algebraic group, the Hopf algebra of the functions on the group totally recapture the object. But for projective variety, for projective object, this is not true. What one can construct a projective embedding and look at the graded ring of the projective embedding. Unfortunately, this ring does not characterize the variety as it is, meaning that same variety, well, it does characterize, but I'm saying same variety may have different rings associated with it that are non-isomorphic graded. But let's not go into it. I have a way to construct a projective embedding. I have a way to build a graded ring, and I will quantize this graded ring. So if I take the special case on homogeneous spaces of a group, which is my case, I have a natural coaction. And for me, a quantum homogeneous variety, projective, is a quantization, a deformation of this algebra OX, which still has a coaction of the quantum group. So, and the coaction, of course, reduces to the correct one when Q is equal 1. So we're looking at rings that are in tandem OQG and CQG. So quantum group and quantum homogeneous variety, which tends to be projective. Okay, so for me, I'm not interested in affine, not because they're not interested, they're very interesting, but in this talk, I will focus on the projective ones. Projective ring cannot be recovered as the invariants. That's impossible. You need the semi-invariants. You need this character. You need the quantization of this T. So let me go to the... So far, so good for the setup. Are we all happy about it? I guess there is happiness. All right. So let me go towards the concept of a quantum section. So suppose we have a line bundle on G mod P, which is fully captured by this magic element T that we saw before. We call quantum section an element not in CG, because T is in CG. We take a quantization, an Hopf algebra CQG, with the same property, exactly the same. You want this element to transform almost group-like, not really group-like. This is D times D, and then you sum the ideal of the parabolic. And then you want that this element, when Q is equal to 1, is back to give you the magic element T, okay, which is in CG. All right. So pi is the projection, and IQP is the ideal of the quantum parabolic subgroup. Okay. We say that a quantum section is the quantization of the line bundle, because if the line bundle is captured by the element T, and we give a quantization D that is having the same property, we say corresponds to such a line bundle. However, this is not satisfactory, because what we want is actually the deformed ring. We want the deformed ring, and we want the coaction. So we define exactly as before. We give it a try. We say, oh, you know, before this definition was working. Before O G mod P was obtained as the sum of all the degree n components, and each degree n component was the function f in the Hopf algebra CQG that was not invariant, but semi-invariant. So it will transform according to T, exactly as before. Now, there is no reason why this should be a ring, no reason why it should be graded, and no reason why it should have a coaction. This is our result. So let me give you the result that this is actually leading to a quantum deformation of the algebra function on G mod P. So this is a theorem shared with Ciccoli and Gavarini. Let's take a quantum section. Then OQ G mod P is indeed a graded subalgebra. So it is a subalgebra of CQG, but the grading is preserved. So this is the first very important fact. Moreover, the sum is direct. This is not difficult. So we have a truly quantization of what we expect of the algebra of G mod P. But not only this, OQG mod P is a graded CQG comodule. So we have a coaction of the quantum group. So we achieved what we expect, that we have a deformation of the algebra of G mod P, and this deformation is in tandem with the deformation of the quantum group, preserving the comodule structure. So we are happy. And in particular, also when Q is equal to 1, I mean, the two specializations agree. This is something that one expects, but it's very nice to have it. Okay, so are we happy with this result? Because now I'm going to see an example, and then I'm going to the more recent work I did based on this result of 2008. And it will be, you know, more complicated because extra structure will come. I guess no. Okay, so OQ G mod P is a projective quantum variety. Okay, so let's see an example of this. So we take a quantization. This is the Manning relations of quantum matrices. If you have seen it, great. If you didn't, that's okay. It just says that you take a ring in the determinants Aij, and you are given a quantum deformation of the matrix by algebra. The matrix co-multiplication is really what you expect. And then you introduce the quantum special linear group, where you quotient by an element of CQMN called the quantum determinant. Is a central element. So when you quotient by determinant -1, nothing bad happens. This is a well-known construction due to many people, including Manning. So it's called the ideal of the Manning relation, but I am aware that many people worked on this besides Manning. And now let us go. Key observation. The determinant D12 is indeed a quantum section. In fact, when you apply identity times pi, the projection, sorry, here should be a bar, D12 bar. So it is landing you in the algebra of the quantum groups times the algebra of the parabolic. So it satisfies the relation of being quantum group. Now, sorry, of being quantum section. Please notice the very interesting point that is no coincidence that the second leg of the co-multiplication, this thing here, is giving you all the determinants of the first two columns. Why is this important? Because these are precisely the coordinates that give you the Plucker embedding. So this quantum sections is really a miracle, same as the T. When you take its co-multiplication, the second leg is, you can look at these elements, and this will give you the generators for the degree 1 elements in the graded algebra. Why are so important? Because when you take a very ample line bundle, as we do in this case, I don't get into this business, but very ample means that it's generated in degree 1. It means that if you tell me these elements, you are telling me the whole story. So you are telling me the whole ring. So it is really a miracle that this quantum section not only gives quantization of the line bundle, but it will give you everything to obtain the graded quantum algebra of the G mod P, quantization of G mod P. This is somehow known in the literature, but I mean, we have to reprove everything because it's not, I mean, it's not a book that you see it, because people don't care about co-multiplication in algebraic geometry. So the Dij, the second leg of the co-multiplication, indeed generates OQGR. And this is exactly what I say. The ring of the quantum Grassmannian is generated by this D12, the quantum section, and then all the quantum determinants subject to the relation, the Klucker relation that you see right here, and their commuting relations. This is a result somehow known, the Klucker, the commutation among the minors. Stefan has worked also on this and many other people, but the fact that you can retrieve all of this in terms of this quantum section is actually original work by me, Ciccoli, and Gavarini. And then in our work, we understand there was a line bundle, but only later on, with joint work with Aschieri and Latini, we fully realized about the power of this quantum section. At that time, it was understood, but not fully. Now we do. Okay. Now, just a quick fact that, of course, if you understand what I told you, the generalization to n dimension is pretty immediate, because if you give me this magic quantum section, then you can generalize. The only thing is that the calculations are going to be more involved, but there is not a conceptual difficulty. So just to give you a feeling, for quantum flags, if you take the full flag, then the quantum section is obtained by all the quantum minors, the principal quantum minors in SLN-C. So you take the quantum SLN-C, you look at all the principal minors, you multiply them together, it is a quantum section. Nice exercise you do in your room. So these determinants generate the flag ring, and you can produce commutation, incidence, and Klucker relations, and you can give this ring. Again, this ring was known before our work, of course. Eckenberger, Kolb, Stefan himself, many people work on this ring, but we have a new perspective through this line bundle embedding. That was the idea of this paper. Okay, so sorry, and of course it comes with natural coaction, because the way we do the quantum section provides us with a natural coaction. Now we go to principal bundles. So far so good. This is the second part of the talk. Stefan, can you confirm me 50 minutes plus 10 of questions? This is what I have?
Yeah, usually what's happening, yeah.
Perfect. Yes, yes, this is the second part. So what we're going to do now is to understand principal bundles. So let me put down the definition. It is exactly what you know from elementary courses. But what we're going to do, we are going to construct a quantization of principal bundles over the quantum projective homogeneous spaces G mod P that we have just described. So we define a P principal bundle. You take, in your favorite category, you want a surjective morphism of topological spaces, algebraic varieties, whatever, differentiable manifolds. You want a free action of the group P on the right, on E, and you want a transitive action on the fiber. We ask local triviality. Sometimes property 4 is not asked, but for us, we get it for free, because these objects, the homogeneous G mod P, have this property. But in general, algebraic principal bundles may not have it. Flaum, that was back, I think, in the 90s, gives a shift theoretic definition of principal bundles with the purpose of quantization. So we look at this definition. He reworks the classical definition. It says, well, for me, a P principal bundle is equivalent, I mean, it proves it for the classical case. For the quantum is just a definition. So I take a sheaf of H comodular algebras. I want a covering where the F ui co-invariant with respect to H is exactly OM ui. Okay? And then you want that locally you have a local triviality property. So the condition number 1 says that M is the basis for the line bundle, for the principal bundle. The second condition is the condition of local triviality. You want a cover of UI where your bundle is trivial. So it splits as a direct product of UI in the base and P in the, which is the fiber. Okay, H is the Hopf algebra corresponding to the fiber. Okay. And why is this Schiff approach interesting? Because you say, you know what, there is a lot of Hopf Galois theory, you know, and then, you know, the canonical map. I mean, many people have described, yes, because these people were interested in the case of an affine base, where you we have a ring that is completely capturing your object, geometric object. But here the situation is very different because for a projective variety like G mod P, so your M is G mod P, there is no ring associated to it because it is a projective variety. So if you take the global sections, they're going to be just the constant. So you really need a Schiff theoretic approach to the concept of principal bundle. Otherwise, you're not able to construct any ring associated to it. Okay. Yes, I forgot to put down, yes, the coinvariance as exactly US. However, remember that any projective variety admits affine cover. And if you restrict yourself to affine rings, then you are very happy. The coinvariants tell you the base and the rings tell you the whole story. So the trick here is the usual trick of algebraic geometry. You speak about very general objects, sheets, and so on, but in the end, what boils down is an affine cover where you speak about rings. And the Schiff condition glues all these rings to give you the full object. Okay, so let us go to the quantum version of this. We take the notion of quantum ringed space that was defined by Manin in his book Topics in Non-Commutative Geometry. So you want M to be a classical topological space. You want OM to be a Schiff of non-commutative algebras. So it is interesting, the notion proposed by Manin, because the topological space is undeformed, and what is deformed is the Schiff of rings over it. If you think about it, somehow it is the same. When you look at the whole ring, you are deforming the ring, the object doesn't appear, so to speak. So this, and I have some work in progress trying to show, but this has been done by many people. So our work is on top of many, Rosenberg, Van Oysted, and so on. We are trying to prove that categorically what we do is perfectly sound. Also, Skoda has a lot of works on this point. He sent me his unpublished paper. So I'm telling you that many people have thought about this notion and what is best. But let us stick with what Flaum proposes and the way we, what can I say, the way we specialize his notion to our setting. So we take a Schiff on the topological space. We call it a quantum principal bundle. If it is a Schiff of H commodule algebras, okay, and principal H commodule algebras, so you want some extra condition, but so faithful flatness essentially, but let's not go into it. We want an open covering so that on this open covering, you retrieve the function on the basis. Sorry, I should have written affine open covering. I apologize. I forgot a very important point. And then you want a locally cleft condition. That actually here is like, okay, I will not comment. This is there is a cleft map, but I will comment later on. I don't want to get into this technicality in this moment. So as you can see, our notion perfectly mimics the Flaum the Flaum definition and the theorem in the classical setting. It simply extends it to the quantum. With an extra little condition about faithful flatness, I will come back to it. it helps for many reasons. So here is the number 1 gives me the base. The number 2 gives me the local triviality. Okay. Now let's see very happily this. I'm going to go fast. Okay. This is the baby example. As you can see, we are looking at SL2C, which is our group G. And then we're looking at the principal bundle, P principal bundle over M, which is G mod P, which is the projective. Perfect. We have two open sets which form an open cover of SL2C. They project to the set UI, and we define a sheaf just on these three open sets. And this is enough for us, because as I say, it is enough to look at this affine cover to retrieve everything. This is, I know it's very generic. You are welcome to ask me a question afterwards, because I have many comments on this point. But this condition, these three formulas will tell us that F is a quantum principal bundle on P1C. And you can show that if you look on these open sets at the invariants, you obtain precisely on the open affine cover of P1C the ring of coordinates. I may have it here. Let's see if I have it here. I don't. I am sorry, I don't have it here, but it's an exercise that you verify local triviality and everything. So this is a key example for us. As you realize, what we're after is generalize this example to the case of G going to G mod P, in the case of P parabolic. So I want to give the example, the quantization, sorry, and this is the quantum ringed space. Okay. Perhaps I go a little fast here because we saw many examples. And this is, again, I saw it for the classical, the quantum is precisely the same. There is no difficulty of anything, the covering and so on. In this baby example, of course. Okay, now the general theory. This is a theorem proved together with my collaborators Aschieri and Latini. Let us pick a quantum section. So we are again in the quantization of G, an algebraic group. So we have an Hopf algebra. And then we fix a parabolic. We have a quantum section, and we assume that the second leg of the quantum section indeed, as the OR, produces an OR family. This is a very strong assumption, I am aware, but as we shall see in a moment, there are some very interesting cases in which this assumption is satisfied. Then, in this assumption, if you look at the subalgebra generated inside OQG by dk di minus 1, so you are taking all the, what can I say, you invert one by one all the determinants, you obtain a quantum ringed space. So this datum is actually giving you a sheaf on the manifold M, which in our example is G mod P. But this is very general. I mean, it's the assignment defines a sheaf you associate to UI. I is a multi-index. We obtain a sheaf of OP comodular algebra on the quantum ringed space, and the co-invariant are exactly the same. So we really have a beautiful situation where everything is happy. The only thing that we cannot show is the local triviality, the existence of a cleaving map, which is convolution invertible, is a certain map of QP to FU1, we don't know. However, if we have just one of them, we can sort of translate it and obtain the local triviality. So in general, we were not able to show, this is a limitation, that this is always a quantum principal bundle because we don't have a local triviality. We cannot prove local triviality. However, if we furtherly ask that on one open set we have the local triviality through a cleaving map, then we obtain the result we have that F is a quantum principal bundle over the quantum ringed space. Okay. Then we produce.
Rita,
Yes, yes, go.
You didn't assume that these OR sets are mutually compatible.
Yes, thank you for the question. Yes, indeed, of course. We have also to assume the very important fact. I apologize for this. I was very synthetic. Being synthetic is being wrong. We are assuming that subsequent or extension do not, if you do one or the other, it does not matter the order. So you have a compatibility condition. Is this what you asked?
Yes, because this is the strongest thing here.
No, I know. Who is speaking? Who is speaking? Sorry.
I think this was Zoran, Rita.
Ah, of course. I'm so glad that you are asking me the clever and difficult question. Thank you for being in the audience. I expect no less, since in your last talk I asked all the questions. All right. So let us look at a special case. We look at quantum matrices, the ideal of the Manning relations again. This is our setup. I'm going very fast. We all know it. And now I produce the following example. So we look at the parabolic subgroup of SLNC, where I take, just one block of dimension 1 and the rest. And this is, of course, inside SLNC. And we know that if we quotient SLNC by this parabolic, we have the projective space Pn minus 1. And this is, we know from different sources that the graded ring of this projective space, is this one. Okay. Now, let us go to reinterpret this very same construction. So we look at the ideal generated by all the elements in the first column of OQG. And then we prove first that if you take D as the first element, A11 in OQG, it is a quantum section. This is very quick to compute. The important thing is that the second leg of the quantum section will give you the coordinate to generate the graded ring for the projective space. So I take the classical open cover. It is really what you expect. So if you take the projective space, there is like an affine cover where you say one coordinate is non-zero. It is really that one, is not another one. And you take the multiplicative sets and you verify that in this case, what Zoran has asked me is actually true, that if you localize, it does not matter the order in which you localize, you get indeed the same ring. So we prove in 2021 with Aschieri and Latini that if you pick this assignment, it defines uniquely a quantum principal bundle on the quantum ringed space. In particular, we show the local triviality, the cleaving map, and all these technicalities that are important, that locally the co-invariants will give you the rings on the open sets and so on. So all these conditions are verified. And this gives us an example. Now, I will spend, so I'm leaving quantum principal bundles as they are to give you quickly some other results, but any questions so far on this example? I guess not. Okay, so what we did at this point is pursue our shift theoretic understanding of quantum projective varieties to construct quantum differential calculus on quantum principal bundle and quantum projective varieties. Okay, so we say that an H covariant first order differential calculus is a bimodule with the C-linear map, which is the quantization of the exterior derivative. We satisfy the Leibniz rule, then the calculus ADA, the image of D, and it has a covariant condition with respect to H. This is well known. This is, for example, one can read the whole story on the work, the book by Beggs and Majid. Now we try to build differential calculus on quantum principal bundles, being aware that there has been ample research on this point. Many people have worked on calculus on principal bundles. There is a long list. I won't even attempt to make this list, but we are different because we consider case in which we do not have a global ring, but we cover our space with open. Okay, so let us take a quantum principal bundle over a quantum space. And then how do we define first order differential calculus? We want D as to be an H comodule natural transformation. So we are mimicking precisely the case of Kähler differentials. Is exactly that. There is no difference with that. We have locally on affine sets the Leibniz rule, and again locally on affine sets the surjectivity FUI d FUI. We need to have it locally because globally this doesn't make really sense. And then the covariance property. Okay, so this is if you open the book by Grothendieck, I was opening it today for different reasons, but this is really what it does. You will find it in EGA 4, section 16. If you're, I was looking at it today, God. But yeah, we're really copying it. We're not we are adapting it to the quantum. And then we now want to construct this first order differential calculus. Let me go a bit quick. You can construct what are called the co-invariant forms because you have a coaction. And you can construct horizontal forms, which are the ones that are killed by vertical vector fields, which are the vector fields coming from the parabolic subgroup. So this is really something very familiar for differential geometers, because this, again, we are mixing up different realms. And then in 2024, we published with Aschieri, Latini, and Weber, that was postdoc in Bologna. We have a first order differential calculus, which is H bicovariant on G, induce an H covariant differential calculus on OQG as quantum principal bundle on the base G mod P. And then we have the very nice situation that the differential calculus on the base is precisely obtained as the co-invariance of H, is precisely the result classical. Moreover, it is the intersection of the co-invariance and the horizontal form. And you have something called the Atiyah sequence that I don't have the time to discuss. It's very interesting, but today's talk, I think, was dense enough. Sorry. And this is the end of my talk. Next slide is the references, which I really want to, to give a credit to the people that work with me. And thank you very much for the attention.
Thank you, Rita. Okay. Right, so we have now time for questions. So are there any questions from the audience? can put your question in the chat if you wish.
Okay, just a moment. Let me. Oh, okay. Where would the chat be? Wait a moment.
Well, there's no
Stop
question
share.
in the chat, so yeah. Okay.
There is no question in the chat. Okay. Right.
I was just checking. Okay, so.
Book by Grothendieck Alrighty, it is called the EGA 4, section 16. He's talking about Kähler differentials. Oh, sorry, I didn't send it to everybody. I apologize. I think I sent a direct message. Sorry. EGA. But is for the ones that I brave at heart, because Stefan, imagine, it's written in French.
Yeah, well, I have no problem with that. I know it's a problem for some people. Yeah. Rita, have you done explicit computation of the differential calculi you're getting in some?
Yes, we do it in our paper, but I figured that today I subject you to too many calculations. I was showing too many formulas, so I decided not to go for it. But yes, in our paper, if you go to the bibliography, I will share the slides with anyone. We compute, of course. Yes.
So what kind of computation can you do? Can you do it for SL2, SL3
so
maybe?
The computation, very good. You're asking me an extremely good question. We did it for SL2 because as soon as you go to higher groups, the differential calculus becomes really complicated. So my student, Junaid, that is here, is working with the Prague group of Wakala and others. Is doing the SL3 case. Okay. Because computationally becomes very tolling. Yeah.
Okay. Are there any other questions?
So perhaps I can attach the slides to the chat if
I think you will. You could, but I think you will be asked. You will receive an email tonight to ask you for the slides. That we will put somewhere. Yeah. Okay. If there are no more questions, then let's thank Rita again for her talk. Thank you, Rita.
Thank you.
And I think the next meeting is next week at same time, same place. So hopefully a lot of people can join next week. Thank you, everyone.
Bye-bye.